All right, folks, we're going to do experiment 2, where you took some of your alcohol, put it in a separatory funnel, threw in HCl, and you made the chloride as a product. So this first clip here, I'm going to try and do IR and NMR as quick as possible in one video clip. So the first part of the procedure, always, you write down the IR functional groups, in this case the starting material. There's only an alkane and alcohol functional group, and we're getting kind of used to this. The only thing that's going to be very obvious is the carbon sp3 hydrogen stretch. If you look in Pavia, you'll see that under alkane and pretty much any other spectra. The other thing you're looking for in the alcohol, the number 1 and 2 things that we should be able to see is the OH stretch and the CO stretch. And of course, it's a tertiary alcohol. So if we quickly go over to your Pavia book, you look in your alcohol section, you quickly review it for yourself, you look at some of their example spectra. Clearly you can see the OH stretch, but the chart that's going to be most helpful is, of course, identifying the OH CO stretch depending on tertiary, secondary, or primary. We have a tertiary, so they're saying the CO stretch would be approximately 1150, and the OH stretch 3620. So we can migrate over to ours. And to be honest, folks, when you look at, this is the spectrum that I obtained for it, 3368. The point is that big absorption rate here obviously is the OH stretch. The corresponding CO stretch, that book was saying 1150 for a tertiary. Now it's interesting, there's absolutely nothing here. So by default, and this stronger absorption here is going to be the CO stretch. So that takes care of the 2 main absorptions for that. As far as your alkane structure, I mean, you can see this peak here in mine, it says 2973, but all of this stuff right here, that is just that side of 3000, that obviously is a carbon sp3 hydrogen stretching. Other than that, I mean, if you really feel like it, you could circle a couple of these peaks just right here and say, it's a CH bend, and that's about it. A lot of these other peaks here, I don't know, there's no definitive thing to circle them with 100% certainty. So then we move on to our product. Obviously, alkane again, and an RX. Now, the interesting thing about these question marks that I have right here is you go to Pavia, and you're looking for, what would be nice is a large collection of sample spectra. So chlorides, they're saying you can have a strong and aliphatic chlorides, but look at the range, 540 to 785. So then I go looking down here. Well, this is tetrachloro. It's related to chloroform, tetrachloromethane, and a CCl stretch, but it's close to 800. But you go back up here and you remind yourself, look at the range. It's huge. So I flip the page, hoping you see something better. This one has 3 chlorines. And yet again, you're still seeing something that's going to fool you to thinking it's in the same place, and that's what, 780. I don't have enough reference spectrum. Would have been nicer if you've seen a primary, meaning 1 chlorine on an alkane, not just this methane molecule. So let's go look at ours. So obviously T-butyl chloride, we'll start off with the alkane. These numbers right here are all this side of 3000, so all of this stuff is a CH stretch of an sp3. This stuff right here, because there's no aromatic ring, you could arguably say that's a CH bend, possibly that as well. You don't have to label that if you don't want to. So now this is what's interesting. Look at my scale. I went all the way down to 450 on that day. Most of your spectra, I've noticed lately, is only at 650. So see, this 570 peak would not be there for most of you. So how many students just automatically circle 810? Now that's higher than the 780 range, right? And most don't have this 570 peak. So all I'm kind of joking about here is the single most definitive characteristic thing for the CLC would have been the stretch, which is here at 570, and most of us don't have it. So it's funny how in this spectra, the only thing that I would arguably definitively circle is this, and I guess we could absolutely circle these here and say it's a CH bend, but that's about it. And as far as what this is, I have no idea what that is for sure. 1158, I have no idea. If you have reference spectra that you can reference and it shows definitively what that is, then fine. Move on, NMR. NMR is such a simple structure. If you're looking at this, clear as day, you can see how 3 methyl groups are the same. There is no hydrogen on that center carbon, there's only one there. So arguably we expect 2 signals, 1 OH hydrogen, and 9, an integral of 9 for these 3. So you look at, this is a reference spectrum that was run actually at the University of Windsor. Let's see if we can get that number. See that giant singlet at 1, it comes out to 8.9, and then that little one, it comes out to 1. So obviously our ratio of 9 to 1 on this particular one that showed both. So we know which one's which, it's simple. This is the carbon 13, and yet again, carbon 13, how many types of carbon? There's 3 methyl groups that are the same, and you have a quaternary carbon, no hydrogen on it, therefore that's going to be Mr. Stubby, very small. So you look at this spectra, that blip is at 77, that's chloroform D. That is obviously that quaternary carbon of our compound, and then those are the methyl groups, the tall one. If you go to the product, it's going to be similar, except even simpler. There's only one signal, 3 equal methyl groups. We should see one giant singlet, and sure enough, that's what we see. And it comes out to be roughly 1.49. Ours, we had 1.46, but it's close enough. We all know what that is. Carbon 13 is going to look very similar to the starting material. You can see the chloroform D at 77. That's the quaternary carbon of our compound in the methyl groups. So that right there is a quick run through of the IR and the NMR for this experiment, which is kind of nice and simple. There's not too much going on.